Welcome! You have encountered some differential equations during the mathematical modeling step of the modeling cycle. In some cases, you could even find solutions of these differential equations. But what would you do if you do not know how to solve these equations? Well, in this video you will learn about direction fields, with which you can sketch solutions to a differential equation. Let us consider our differential equation. The derivative of a population of rainbow fish P with respect to time, T, equals 0.7 times the population size P minus a constant 20. The population P has as unit the number of rainbow fish and the time T is in days. This indicates that the unit of 0.7 is per day and the 20 is in number of fish per day. As you can see, the right-hand side of the differential equation does not depend on the time t. This is an example of a so-called autonomous differential equation. If you know the number of rainbow fish p, you can use the differential equation to calculate the rate of change of p per day at that moment. So for example, if p equals 30 at time t is 0, you get that the rate of change of p equals 1 per day. P will grow slowly. If however the number of rainbow fish is 20, P changes per day at a rate of -6 per day. P will decrease fast. If we calculate the rates of change for many population sizes P and different times T, we can sketch the direction field. So now let me first tell you what a direction field is. A direction field for a single differential equation is a graph with as horizontal axis the independent variable, which for our equation is the time t, and as vertical axis the dependent variable. So for us this is the population size p. A direction field contains a lot of small arrows. The slope of these arrows indicate how fast the value of the dependent variable changes when the independent variable increases. In our case, how fast population p changes when the time t increases. The slope of the arrow equals the derivative of p with respect to time. Now let us draw the direction field together. First, draw the axis you need. Now consider t equals 0, which is the initial time, and we start with 40 fish. The rate of change of p is then 8. So your first arrow must have a slope of 8 per day. You draw a small arrow with slope 8 per day through the point 0, 40. Now take a different initial value of p. Let us say 30. This will give a slope of 1 for the arrow, which is less steep than the slope of the first arrow. Another initial value for p is 20, which gives this arrow. As you can see, the arrow points down, so the rate of change apparently is negative. Do you agree with this? Let us also add the arrows for the initial populations of 10, 50 and 60. Do you already see a pattern in the arrows? Now we have drawn arrows at time 0, we can try to draw a few arrows at a different time. But because our differential equation is autonomous, the derivative of the population with respect to time stays the same for all times. So you can simply copy the first 6 arrows to different times. There is still some room between and above the arrows, so let us add a few more arrows in between. Now we have constructed a direction field and we are ready for the next step, sketching solutions. Say, for example, that you have 30 fish initially at time 0. In the direction field, you see that the arrow at this point is pointing upwards with slope 1 per day. This means that if we increase the time by 2 days, the value of p will increase with 2 fishes. If you put your pen at the initial point and draw a very small line with slope 1 starting at this point, you leave the point and come close to another arrow. But this means that the slope of your curve should be more and more like the second arrow as you let t increase. So you should change the slope of your curve as you are drawing your line. If you go further, you will come close to another arrow. So you must follow the slope of this arrow. This of course repeats, which gives you this curve. This curve is a sketch of the solution. It is not yet an exact solution to the differential equation, but it gives you an idea of what the solution may look like if you start with the initial value 30. If you choose a different initial condition, for example 20, you get a second solution curve. If you repeat this for many different initial values, you get a graph like this. Can you differentiate the different behaviors of the curves in this graph? Next, you will sketch the direction fields and approximate solutions yourself for some other differential equations.